Welcome to this explainer. Okay, so I want you to look around you for a second. The buildings we work in, the bridges we drive over, literally the roof over your head right now, they're all standing firm against gravity. But how? Today, we're diving into the invisible math of structures, and specifically, we're focusing on sectional properties. Now, I know that sounds like a super dense engineering term, but I promise you, it's actually incredibly fascinating. It's kind of the secret language of physical balance and strength that quite literally holds our modern world together.
So how do engineers actually know a beam isn't just going to bend? When you put a massive amount of weight on a steel beam suspended way up in the air, why doesn't it just fold right in half? Well, it's not magic. And surprisingly, it's actually not just about throwing more, heavier material at the problem. Check this out. The Eiffel Tower is so perfectly engineered that if you melted down all of its iron, it would form a solid base layer only about 2.5 inches deep. I mean, no way, right? How is that even possible? It's entirely about the geometry of the shape itself. Long before anyone pours a single drop of concrete or welds a piece of steel, they run the math. Let's find out exactly how they do it.
Here's a quick roadmap of where we're headed. First, finding the balancing point. Then, tackling composite shapes. Next, resistance to bending. After that, twisting and axis theorems. And finally, we'll wrap up by calculating structural sections.
All right, let's jump straight into Section 1, finding the balancing point, focusing on first moments and centroids.
Imagine a generic, kind of potato-like shape plotted on a graph. Now, please don't let the calculus setup intimidate you here. That little piece labeled dA is just a tiny, microscopic slice of the entire area. And that dashed line y? That's simply the perpendicular distance from the horizontal axis up to that tiny slice. If you multiply that tiny area by its distance, so y times dA, you get what engineers call the first moment of area. You're basically just measuring how much that specific little piece influences the balance of the whole shape relative to that axis.
And that brings us to a really crucial concept, the centroid. By finding the first moment of area for every single tiny slice and then adding them all up, which, by the way, is all integration really is, we find the shape's theoretical balancing point. If you were to cut this exact shape out of a piece of stiff cardboard and try to balance it perfectly on the tip of a pencil, the exact point where it rests perfectly flat without tipping over, that's the centroid. By definition, any axis passing right through this centroid has a first moment of area of exactly 0. It's in absolute perfect equilibrium.
Moving right along to Section 2, tackling composite shapes. Let's get into some real-world geometry.
Because in reality, steel beams and concrete columns aren't just generic, simple blobs. They're rarely a single C-channel. Usually they're much more complex, composite shapes, like a Z-section, made up of several regular geometric pieces that are fastened, welded, or rolled together. To calculate the centroid, that vital balancing point we just talked about, for these messy shapes, we obviously can't just guess by eyeballing it. We need a really reliable, repeatable system.
So engineers rely on a totally foolproof 4-step methodology to figure this out. First, they visually divide the complex section into simple geometric areas, like rectangles, where the individual centroid is super obvious. Second, they choose a convenient set of reference axes, basically establishing a starting zero line for x and y. Third, they determine the surface area of each individual segment. And finally, step 4, they calculate the coordinates of the master composite centroid by just averaging the first moments of all those smaller areas together. It is such an incredibly elegant way of breaking a massive, scary-looking problem into bite-sized, totally solvable pieces.
Next up is Section 3, resistance to bending. This brings us to the second moment.
The mathematical contrast here is actually fascinating. So we just talked about the first moment of area, which uses the integral of y times dA to find that balancing point. But compare that with the second moment of area. The only mathematical difference here is that we square the distance, so it becomes y squared times dA. By squaring that distance, we drastically amplify the mathematical importance of any material that's located further away from the center. This second moment of area, it's also known as the moment of inertia, and it's the exact definitive metric of a shape's structural stiffness.
Notice how the calculation for our tiny blue element is now entirely concerned with the distance squared. What this tells us in the real physical world is that material placed farther away from the centroid provides exponentially more resistance to bending. I mean, this is exactly why an I-beam is shaped like a capital I. It pushes as much steel as physically possible far away from the center balancing point, maximizing that distance squared to create immense stiffness. And it does it all without making the beam completely solid, heavy, and wasteful.
And that naturally brings us to this highly useful concept, the radius of gyration. You can think of this as a brilliant theoretical shortcut.
Imagine taking the entire cross-sectional area of a really complex shape and magically compressing it down into a single, infinitely thin strip. The radius of gyration is the theoretical distance from the axis where you could place that heavily concentrated strip to get the exact same moment of inertia, the exact same bending resistance as the original messy shape. It condenses all that complex geometry into one single, highly powerful number for an engineer to work with.
All right, Section 4, Twisting and Axis Theorems. This is basically the engineer's toolkit.
Now, before we tackle the big mathematical shortcuts, consider a circular shaft for a moment. Not all forces in the real world make a beam bend, right? Sometimes forces make things twist. Think of the drive shaft in a car. This twisting action is called torsion. To calculate how much a shape resists twisting, we use something called the polar moments of area. Instead of measuring the distance to a flat x or y line, we look at a tiny ring at a radius r radiating out from the very center point, the z-axis. By integrating this across the whole circle, we find out exactly how much a solid shaft or a hollow pipe will fight back against being twisted.
Which brilliantly illustrates our first major shortcut, the perpendicular axis theorem. This theorem states that the twisting resistance, which we label Iz, is exactly equal to the sum of the bending resistances about the two mutually perpendicular axes, so Ixx plus Iyy. What does that actually mean? It means if an engineer already knows how hard it is to bend a specific shape horizontally and how hard it is to bend it vertically, they don't have to do any new, complicated calculus to figure out how hard it is to twist. They literally just add the two bending numbers together. It's a total game changer.
And this builds directly into the parallel axis theorem, which is arguably the most vital, time-saving shortcut in all of structural engineering. Say you already know the stiffness around the center centroidal axis, labeled GG. But your specific design requires you to know the stiffness around a totally different axis, down at the bottom, labeled XX. Instead of redoing all that complex math from scratch, you just take the stiffness at the center and add the total area multiplied by the perpendicular distance between the two parallel axes, squared. So Ixx equals Igg plus area times y squared. It lets engineers shift their complex calculations anywhere in space completely effortlessly.
Let's move to our final segment, Section 5, Calculating Structural Sections. It's time to put it all together.
To prove the immense strength of the common structural steel shapes that literally make up our cities, an engineer has to combine all these tools we just went over. Take a composite I-beam, for example. They divide it into 3 rectangles: the top flange, the middle vertical web, and the bottom flange. They find the exact centroid of each individual piece. Then, using that incredibly powerful parallel axis theorem we just talked about, they calculate the moment of inertia for each piece, relative to the entire overall shape's center, and they sum them all up. This final, unified number is the ultimate mathematical proof of the beam's immense strength. It's what ensures that a bridge or a skyscraper won't just stand up, but will be perfectly safe under load.
Well, thanks for joining me on this explainer. The next time you're walking through a busy city, I want you to look up. Remember that it's not just brute force, heavy steel, and poured concrete keeping those towers reaching into the sky. It is precise, invisible, and honestly, truly beautiful mathematics. So I'll leave you with this. If simply rearranging a shape's cross-sectional layout, like moving material to the extreme outer edges of an I-beam, drastically alters its strength and stiffness without adding a single ounce of extra material, what other hidden geometry is holding up the physical world around you?